All right, so we need to talk about a fun little concept called a zero force member. All right, and zero force members are things that are added into the truss for stability, uh, but in the normal circumstances, hold very little force. And in our model, they hold zero. In reality, as you have slight deflection in the truss, they will hold a little bit of force in them, but they're basically just there to stabilize the beam structure. Okay? So, we have two cases of zero force members, so allow me to do a couple drawings and try to set this up. So here's a truss, like so. So it's pinned to the wall, okay, and here is a load, okay. So picture this is just kind of a loading dock here. So we have this truss and something's hanging off of it. Well, suppose for some reason, why I don't know, but just suppose, somebody came along and said, I'm going to add two members to this. Right here. So I'm going to add a member on here that goes out here and a member on here that goes out there. And so what we have here are two members that have, notice there's no load on this, there's no P or anything here. No load, they're just two members going out into space. Okay, with no support reaction, so these members connected to the support, there's support reactions here. So we have two members out in space, no load, seemingly doing nothing. Well, they are doing nothing. They're doing absolutely nothing. So try to picture this. These are two force members, so there's a force going along this line and a force going along that line. All right. Is there any way that these two forces can sum to zero? And since they're not parallel, the answer is no. It just can't happen. All right. So since we know this thing is geometrically stable, so it's not falling apart, rolling someplace, that tells you, knowing this is in equilibrium, it means there's no forces going through here. Because if there were forces going through here, then the sum of forces would not be zero, and this thing would be walking off the cliff. And that's not happening. So we have a rule for that. This is known as Rule 1. And so it basically says if only, let me make life easier for us. No, I'll just write it out. If only two members form a truss joint, okay, with no external load or support reaction. So it's just two members by themselves out in space, then the members are zero force members. There is no structural force going through them at the moment. So that's case one. Case two. Consider the following. So a simple truss. So I have a bridge here. All right. And just adding to the truss. All right. And we'll put a load here. Call it P. All right. We'll let this be A. Let that be B. C, D. That's a P. All right. And let's look at this right here. All right. So if I look what's happening, and I analyze what's going on over here, if there's a force, say, coming down, as this thing comes down, there'll be a force coming down through this member. All right. And I have my supports here can do stuff. And since this is going to the left, this can be going off to the other side. And they can have supports here. And it can all equalize out. All right. So that's, I'm trying to say there's nothing wrong here. And likewise, you put a force through here. The force can work its way down. This can come back, what have you. We can have support there. It all works out. What's happening here? All right. If there is any force coming down through here, there'll be force here in this horizontal piece. But this is straight up and down piece. If there is any force in this vertical piece that comes down into here, how can these two horizontals equalize it out? Some forces in the y, you're going to get a non-zero term. If this isn't moving, that has to be 0. Now, the exception is that let's say you had a load there. Well, then this and that load, I'll put a P there, that could equalize out. But if there's no load here, this has to be a 0 force member. This is just there for stability. That's all it's doing. All right. Kind of keeps all the parts, so it keeps these things from suddenly get a little perturbation and having them go wing like that. So it provides stability, but it has no, in terms of structural strength, not doing anything. That's the point we want to get across. So anytime you see two members connected in a line and a third oblique member comes into them where it's not at a support and there's no load, this must be a 0 force member. So in writing, if three members form a truss joint. All right, with two members collinear, and no load at the joint, the third member, oops, didn't spell that right, member is a 0 force member. Boom. If you don't follow that, we'll have a problem where we'll have a few of them. So here's our next problem. Right here. So what I have is a gantry system, and it is held to the wall. So this is the pin holding it up. Here's an expansion joint, and we have all this truss, and at the top pin it's connected to a wheel, a pulley, and there's a mass here hanging, and it goes over the pulley, and the cord continues, and it is also connected to the wall via pin. All right, so if you look at what's happening here, a little more detail. The radius of the wheel, r equals 0.1 meters. So that's why you're seeing the pin is located there, and then here's the cord coming off the top. So that's this dimension here, this extra 0.1, because r is 0.1. All right. So the question in this problem is, what's the largest mass here that we can put on it such that when you look at all these members in here, no member is more than 30 kilonewtons in tension and 25 kilonewtons in compression. So it's a little open-ended. All right, we'll start knocking it off. First thing we need to do is kind of figure out what's happening up at this wheel. So we're just going to do a quick examination of the pulley. So here's the pulley, and the pulley is connected to the pin. So if you look at what's happening here, so there'll be some weight, and this is there'll be constant tension in the line. So if there's W here, there's got to be W there, and so that's just constant tension going through the line. If you look at that from a torque point of view, these now have no net torque here on the wheel to make a turn. Okay, and so and then there's a pin here that'll be pushing on the wheel, and so I'll just assume those are positive, dx, dy. This is up at D, so pin at D here. And so if you look at this, what you see is dxw, dyw, everything just cancels out. So w, the weight, that whatever this weight is equal to dx is equal to dy. That's useful. All right. So let's move this over to the side here. And let's start analyzing. So here I have my truss. I'm going to start analyzing that. So if the pins push here on the wheel will push back equal and opposite, and that's what I'm having here up at D. So that's the effect of the weight going this way and that way up at this top point. All right. So the first thing I'm going to do is I'm just going to evaluate what are my supports doing. All right. So if we look over here, this is G. All right, and so there's a pin there, so I'm going to say, let's see, I'll just draw GX going here. This is a pin support, so it can go in two directions. This can only push out, so I'll put in an AX here. Here's A, and so something's got to hold this thing up, so seems to me that GY has to be going that way. Okay? So if we sum the moments at G, here, summing the moments at G, I'm going to take the moments here, that wipes them out. All right? So I have, let's see, W, that's 3.5 meters up. And that looks counterclockwise, so I have W times 3.5. And here's W, and that's 6. That's going clockwise, minus W times 6. And AX, that's 2.5 meters down, and that's going counterclockwise, so that's positive. A times 2.5. All right? And that's all there is, equals 0. Solve for A, and you would find, or AX, you need to find AX is equal to W. All right, so let's look at this. So this is AX equals W. So I have W going this way, W going that way. That means GX equals 0. Okay, and here's W going down, so GY is going up. So GY is equal to the weight of whatever's hanging there. And we're treating all of this stuff as being massless in there. Obviously, that'd have to support it as well. All right, so we know what the supports are doing. So when you do these problems, before we start going in and looking at all the joints, what one normally does is says, are there any ZFMs? Zero force members. Okay, well, let's just analyze this thing here. So we're going to go back to this thing. Now, so notice what we have here. I have a line. This piece, that piece. Okay, they're in a line, and this is coming in oblique. All right. So if there's force in here and there's force in here, if there's any force in here, in EC, is there any way, so this is 3 members. Over here I have 1, 2, 3, 4 members, so we don't care about that one. So here I have 3 members, 1, 2, 3. 2 are in a line. This one comes in. If there's any force in this, can these 2 wipe it out? No. So that says that's a zero force member. So that's as if that wasn't even there. So that's gone. Well, now I have 1, 2, 3 members. This is zero force member, so there's nothing there. So if there's any force in these, this is coming in oblique. Can anything equalize it? No, that's gone. So now this is 1, 2, 3. Same argument. That makes this 1, 2, 3. Same argument. Bottom line is that we have a lot of zero force members. EC, FC, FB, and GB. All right? We have wiped out all of these things. They're all zero. We don't have to pay any attention to them. So all that's left is this long thing, that long thing, whatever force is going through each of them, and of course this piece over here. So it's kind of wild. All of a sudden we've wiped out kind of everything. All right. So let's see. Let's check my next page where I'm going to go here. Yep, let's set that up. All right. So the next thing I'm going to do, I'm going to leave this page where you can kind of see it. I'm going to go up to D and analyze what's going on. All right. So if you looked up here, so here's ED, and I have DC. All right, so this is coming up, but if you look at what's happening, 2.5 plus 3.5 is 6, and that's 6. So this is at 45 degrees. This other piece here, that would be 6 and 3.5, and so if you analyze that, that's 30.26 degrees. All right, just for sake of argument here. So I know this is, the pin is pushing down, and then these are the members pushing back. What can we say? Well, let's figure it out. Let's see here. If you sum forces in the x, set that equal to 0, one would come up with, let's see, minus x, or minus w. Then I have FED plus FED cos of 30.26 plus FCD relative to this side, that would be sine of 45. On that side, it would be cos 45, but both are 0.707, whichever way you want to look at it, and you set that equal to 0. Okay, and I left a minus sign off here for some stupid reason. All right, summing forces in the y. Set that equal to 0. I have a negative w. No problem. FCD is going up. So, well, let's just do FED first. So FED would be plus FED sine of 30.26 degrees. Plus FCD is going up. FCD, take the cosine in this case, 45. Set that all equal to 0 again there. All right. If you look at this, I have two equations and two unknowns. Sort of. Let's see what we have here. How are we going to solve this? Well, if we let's bring the w's to the other side. So let's just set this up. FED cos of 30.26 plus FCD 0.7071 equals W. All right. FED sine of 30.26 plus FCD 0.7071 equals W. All right. Well, how are we going to solve this thing? So what I'm going to do is I'm going to take this equation and subtract this from it. So I'm going to have FED cos 30.26 minus FED sine of 30.26 equals 0. I'm just taking this minus that. And I do that, I'm left with this equation. So since sine, cosine, and sine are not equal, except at 45 degrees, the only way this equals 0 is if FED is 0. Oh my goodness. So let's go back to our picture here. So that says this is a zero force member. Well, if that's a zero force member, then that one is. Then that one is. So I've wiped out all of them. I'll put in little zeros. Okay? So these in here were obvious. This wasn't obvious. It's kind of surprising, actually. Okay? Now you can see how all of these help stabilize these things so they can stay in a line. But in terms of holding major structural load, no, none. All right. So FED equals 0. All right. So if FED equals 0, we can go up here and wipe this term out here. And so we have FCD 0.7071 equals W. Well, we're left with FCD equals 1.414 times weight. And it's all positive. So you can see we were showing compression of the pin. So we have compression. All right. So if FCD is 1.414, then FBC is 1.414 W. And now we know FAB is bringing the compression all the way down, 1.414 W. All right? Now, and if you look at this, let's see how that worked out. 1.414 W times 0.707 would give us W. W going to the left, here we have W going to the right, everything checks. If I take the sign, this is the same difference, 0.707, it says I have W here going down. That means FAG is W. It's just simply the weight of what's hanging there. Okay? So, now we know what everything is. We just simply have to take a look at our limits. So, to take a look at our limits here, note FAG is in tension. Put our T there. So what were our limits? Relative to tension, we had 30 kilonewtons. All right. And so that would say the weight can be, equating this, be 30 kilonewtons. For compression, though, we had 25 kilonewtons, and this is in compression, right here, equal 1.414 W. Divide through the 1.414, we get W can be 1,860 newtons, which is a smaller amount. Or we could say 17.86 kilonewtons. All the same difference. Okay? And we've solved our problem. This is a fun problem. It's all dealing with zero force members where you wind up with 1, 2, 3, 4, 5, 6, 7 of them. And just looking at it, you probably, when you started this, would never have thought that. Okay? Now that you know what's going on, you would have guessed the ones in the middle, the ones along this far edge. Yeah, that wasn't obvious at all. Just a coincidence of how the structure of the gantry was set up. All right, we'll do a bunch more of these following this. Bye for now.